Hello everyone. Today we're going to discuss about propositional equivalences. Section 1.3 Introduction. Usually we replace mathematical statement with another statement of the same truth value. Method that produces statements with the same truth values from given compound statements are used in the construction of mathematical arguments. Definition: a compound proposition that is always true no matter what the true values of propositional variable that occur in it is called a tautology. A compound proposition that is always false is called a contradiction. A compound proposition that is neither a tautology nor a contradiction is contingency. Example 1. Show that the proposition form of P union negative P is a tautology, while the proposition form of P intersected with negative P is a contradiction. I have two ways of proving an argument. I can either use a truth table or I can use some rules that we will see later on. These rules we can prove that an argument is a tautology or it's a contradiction. So here we use a truth table to prove that these two arguments, the first one is a tautology because every time I'm getting true from from the truth table, and the other one is a contradiction because I'm getting F every time I'm using the truth table to prove it. Logical equivalences. Compound statements that have the same truth values in all possible cases are called logically equivalent. Definition: the compound proposition P and Q are called logically equivalent if P and Q, the biconditional statement of P and Q is a tautology. The notation P equal to Q, where the equal here consists of three layers of three lines on top of each other. This denotes that these two statements are equivalent. So we use the equivalent sign that we are going to be using is either an arrow sign that that pointed into two directions, or an equal sign that have three lines. De Morgan's law. First law of De Morgan states the following: when we apply negation into a joint statement, negative open parentheses P and Q is equivalent to finding a disjoint statement of negative P or negative Q. The same thing in the second law. It says that when we apply a negation into a disjoint statement, we find a joint statement. In mathematical terms, negative open parentheses P or Q close parentheses is equivalent to negative P and negative Q. So we can prove both laws using truth table, as we can see below. Equivalent statement. Implication and contrapositive are equivalent. Also, converse and inverse are equivalent. So please see the truth table below. Equivalence is very useful. If, for example, we have a complicated proposition and it has an equivalent proposition which is simple, we can replace the complicated proposition with the simple proposition. So this is how equivalences are important. Proving equivalences with truth tables. We can prove equivalences using truth tables, but tables become very big for complex proposition. Therefore, we need a different technique for proving equivalences of larger proposition. In the following slide, we will see different approaches of proving equivalences. So this table is actually extracted from your textbook. So you see here logical equivalence laws. You have different laws with different names. So you see here a statement and its equivalent. We can use these laws to simplify complicated proposition or compound proposition. This is also these are also tables that we can use to simplify or to find equivalences of compound statements. Just like like what you have known in trig identities. So these equivalences work just like trig identities. When you have a very complicated trig expression, you can use trig identities and simplify it. We use the same techniques here. Equivalent proofs. To prove that A is equivalent to B, we produce a series of equivalences beginning with A and ending with B. Sometimes we can produce a series of equivalences beginning with B and we end up with A. Usually we choose the most complicated side to start with. Example number 2. You are asked to prove if the statement negative open parentheses P or open parentheses negative P and Q close parentheses is equivalent to negative P and negative Q. So you are asked to find the to prove that these two statements are equivalent. As you can see here, so the first thing is we use the De Morgan's second law. Here I have negative outside the parentheses. When I apply negative into an OR expression, I get an AND expression. Okay, again, when I use the first law, because here if I use the first law for the inner part of this expression, then I get also for an AND expression I get an OR expression. Okay, using the double negation, I have double negation here, negative and negative twice, that become a positive, so it become positive P. By using the distribution property, now I get a simpler expression. And then again by using the commutative law for disjoint, so and then from there I get using negative Q and negative Q by the identity law, we get F. So these two statements here are equivalent. This two statement is F. The second part of the statement, or the second statement on the right, is F, and then the other statement also we prove that the other statement is F. So both of them are equivalent. In example 3, we want to prove the mathematical statement, that this mathematical statement here is a tautology. That means it's always true. In other words, if open parentheses P and Q, then P or Q. So we want to say that this statement is always true. So we also use the same laws from the table that we discussed early, and then we can prove that this is always a tautology. So in the table, an implication can be turned into OR expression. It's the first thing we did. And then once we have the OR expression, with the OR expression by first law of De Morgan, we can do more simplification. And then by associative and commutative laws, we can also reduce the statement into truth or true. So true or true is always true. So lastly, we can see our references.